Last day we talked about sequences of numbers. We talked about them being defined explicitly and defined recursively. We took some examples, we wrote out a few terms, and then we reversed the process. I gave you a few terms, and we found a formula that represented those terms. We introduced the idea of a limit of a sequence. We say that a sequence whose terms are denoted by C sub n, the only kind of limit we can take is a limit as n goes to infinity, and if that limit exists, we call it L. What we mean by that is, if you watch the terms in the sequence are getting closer and closer to some number, staying close to that number as n gets bigger and bigger and bigger. And again, that's the only kind of limit that we can talk about for sequences. Not like in calculus, where you can talk about the limit as x goes to just about anything. Sequences, only limit as n goes to infinity. And we considered a number of rather straightforward examples. I'd like to consider today some more difficult ones. First example, the following. We say that the limit of the sequence is L. We also say that the sequence converges to L. That's just different ways of saying the same thing. So consider the following sequence and talk about whether it's got a limit. N squared, 2n minus 3 over 3n squared. So don't need those parentheses. But I need big ones. A little more complicated than last day, but we can break it down into pieces. I would suggest we talk about the limit of this one as n goes to infinity, and then we talk about the limit of this one as n goes to infinity. If those limits exist, then there's a theorem that says we can multiply those two limits together to get the limit of the sequence as a whole. So let's look at the pieces. The limit as n goes to infinity of n squared, 2n minus 3 over 3n squared plus n minus 5. In first year calculus, you would have the same kind of limit, but it would be x going to infinity. And you learned then, we saw that same thing happening last day, if you divide top and bottom by n squared, you get 1, 2 over n, 3 over n squared, 3, 1 over n minus 5 over n squared. And now the limit becomes transparent. As n goes to infinity, that guy goes to 0, that guy gets close to 0, that guy goes to 0, that guy goes to 0. And all you're left with then is an answer of 1/3. That one is straightforward. I've been often asked the question, could I use L'Hopital's rule instead of doing that division top and bottom by n squared? The answer is yes, but you have to be careful. So let's take a slight digression and consider talking about the limit. As n goes to infinity, it's that same thing. N squared plus 3n minus 3 over 3n squared plus n minus 5. You cannot use L'Hopital's rule on that limit. Why? Because L'Hopital's rule involves differentiation. What you do in L'Hopital's rule, it goes for x's, you differentiate the top with respect to x, you differentiate the bottom with respect to x, and get to that limit. You can't differentiate a sequence. Because remember, sequence is only defined for n equal 1, 2, 3, 4, 5. Differentiation doesn't make sense. So don't ever try and do L'Hopital's rule on that. But there is a way around it. Suppose I wrote down instead this same limit as x goes to infinity of x squared plus 3x minus 3 over 3x squared plus x minus 5. Can I use L'Hopital's rule on that? The answer is yes. But then the question is the limit of the sequence going to be the same as the limit of the function? And the answer is yes. If the limit of the function exists, then the limit of the sequence will be exactly the same thing. Period. Right. And the reason is the following. If you were to draw a graph of this function, suppose it looks like this, and suppose it were to approach 1/3. Right? 1/3. Suppose you use L'Hopital's rule to prove that. So there's the function. Where's the sequence? Well, the sequence is a bunch of dots. That dot, that dot, that dot, and so on. If that curve approaches 1/3, then those dots have to approach 1/3 also. In other words, you can use L'Hopital's rule and say that if the limit of this thing exists, then this will have the same value. Now don't take this too far. If this limit does not exist, you can't say anything about that one. Clear? Right? You can't. But this one, if we use L'Hopital's rule on this one, you say differentiate the top with respect to x and you get 2x plus 3. You differentiate the bottom and you get 6x plus 1. You use L'Hopital's rule again. Limit as x goes to infinity of 2 over 6, and that is 1/3. And therefore, this limit is 1/3. So L'Hopital's rule can be used, but you've got to convert from n's to x's in order to do so. So don't ever, on an exam, use L'Hopital's rule on this, because I will mark it wrong. You can't do it. Okay? All right. So this one we got without L'Hopital's rule, but again, you could, as long as you go over and do that kind of thing, replace the n's by x's. All right, back to this question. What about this piece? What about the limit of that one? Well, if we look inside here, what does that part do as n goes to infinity? Well, it's reasonably clear, but you can do the same kind of thing. And since you got n squareds on the top and you only have n's on the bottom, that part is going to go huge, going to approach infinity. And so you're asking then, what is the angle whose tangent is infinity? And the answer is pi by 2. So we're going to get then that the limit that this sequence is going to approach 1/3 for that one, pi over 2 for that one. So final answer, pi over 6. Remember this capital T from your first year calculus course? That means you must choose principal values. The principal values of the inverse tan are between minus pi by 2 and pi by 2. You need to be able to do that for all. I can put any trig function, inverse trig function here I want, and you need to know the principal values of those inverse trig functions. So there's one that's a little bit complicated looking, but when we broke it down, it wasn't too bad. Suppose I gave you this one. Oh, by the way, I've seen people do the following. Say the following kind of thing. Well, if I want this limit, if n is getting huge, who cares about minus 3? If you plug in here a billion, you get a billion squared plus 2 billion minus 3. Who cares about the 3? Similar reasoning, who cares about the 5? So we'll simplify the problem by just ignoring those guys. You might carry that further and say, well, if this is 10 billion squared and this is 2 times 10 billion, that one is not really size-wise compared to this one here. This guy is the dominant guy. So why don't we just kind of ignore and ignore and ignore and ignore and say we're left with n squared over 3n squared, and that's 1 over 3. Ha! See? 1/3. I would tell you or suggest you don't do that kind of reasoning. It sometimes works. It did here. Other problems will work, but there are problems where it doesn't work. For instance, suppose I gave you the following sequence. root of n squared plus 3n minus 5 minus the square root of n squared plus 4, and said, you go find me the limit of this sequence if it exists. If the limit exists, we say the sequence converges to. If we say the limit does not exist, we all say that the sequence diverges. So question, does this sequence converge? If it does, what does it converge to? If it doesn't, then it diverges. Well, if you use this kind of reasoning, you might say, cover the 4, cover the 5, cover the 3n, and the answer is 0. Because then you get square root of n squared minus square root of n squared. That's not right. So here you can't do it, and there you could. Am I going to tell you when you can do it, when you can't? No. I'm suggesting don't use that kind of reasoning. Well, you did this kind of a limit in first year, and you may recall that the trick was to rationalize that expression. That is, multiply the top and the bottom by exactly the same thing, but put in a plus sign instead. So write the limit as n goes to infinity of square root n squared 3n minus 5 minus the square root of n squared plus 4. Multiply that by top and bottom by exactly the same thing, n squared 3n minus 5n minus 5 plus the square root of n squared plus 4. If we do the multiplication, well, by the way, do not drop limit signs. I see that so many times. But people just kind of don't bother writing them. That's not correct, and it's not good English. Just don't do it. So if we multiply, this is like a minus b, a plus b. So you get this one squared minus that one squared. So you're going to get n squared, 3n minus 5, minus n squared plus 4, over the bottom. And we have rationalized the numerator. That's what we said. With rationalizing the numerator, all that's happened is the square roots have gone from the numerator to the denominator. But watch what happens. Equals the limit as n plus 1. Not by anything yet. Notice that I can cancel that with that. Left on top with 3n minus 9 over the bottom. So we now have to take a look at this limit. Don't do the cover-up stuff and say ignorable. But this one, suppose I pull that same kind of procedure we did here and say what I would like to do is I'm going to divide the top and the bottom by n. Divide the top by n, and what do I get? 3 minus 9 over n. Going to divide the bottom by n. Going to divide this by n. Going to divide that by n. To divide this by n, I'm just going to write it here so you can see it. And I'm going to put the n under here. I'm going to take that n inside the square root. If you bring it inside the square root, it becomes n squared. So if I take and bring it inside, then I'll get the square root of 1 plus 3 over n minus 5 over n squared. Plus, same thing here, take it inside, 1 plus 4 over n squared. Does it now become clear what the limit is? As n gets huge, that goes to 0. That goes to 0. That gets to 0. That goes to 0. And so what do you left with? A 3 on the top, square root of 1, square root of 1, 3 over 2. So the answer to this limit is 3 over 2. And there's no way that you can look at that and say, ha, I can see that. It's 3 over 2. There's just no way you can see that at all. Right? So this was a trick you learned in first year for functions. It works for sequences as well. Consider this one. Limit n going to infinity, 1 over n to the n. What do you think that limit is? I would be willing to bet that the vast majority of you would tell me that the limit is 1. Reasoning being is saying, well, as n gets huge, this goes to 0, and you'd have 1 to the infinity, and that's 1. And nothing could be further from the truth. Now, what I often tell people to do when it comes to sequences and series, write out a few terms of the sequence or series to get an idea of what the terms look like. That might help you. If you look at the first term of this sequence, you put in n equal to 1. You get 1 plus a half to the 1. 3 halves. So the first term is 3 halves. You want the second term, you put in 2. 1 plus a half. That's 3 halves squared, which is equal to 9 over 4. And the thing to notice is that one is bigger than this one. What if we look at the next one, the third one? We get 1 plus a third, that's 4/3 cubed, which is 64 over 27. And you pull on a calculator, this one's bigger than that one. Now, if you saw that, what would make you think that these terms are approaching 1 when they seem to be getting bigger? Now, it is possible that after a while, they stop getting bigger and start to get smaller, but I just don't think that's going to happen. So what are we going to do with this limit? Well, the answer is you should know what it is. You had it in first year calculus. That's the definition of E. Which is about 2.71828. And you can kind of see that. Here you got 1.5, 2.25, and this is bigger. Yeah, they're getting bigger. Right? And they continue to get bigger forever. That's not an easy thing to prove. But they do get bigger and bigger, and they approach E. Remember that. I've seen this on many, many tests and exams, and somewhere buried in the problem is this fact that the limit of the sequence is E. Remember it. So there's somewhat more complicated limits than the ones we saw last day. Let me ask you the following question. If the limit of a sequence exists and is equal to L, what do you think about the following idea? Would you think that the difference between successive terms will get closer and closer to 0? That is, the terms will get closer and closer and closer together. If they're approaching L, would they be getting closer and closer and closer to each other? That is, to put that, mathematically we could say that the limit as n approaches infinity of c sub n plus 1 minus c sub n is equal to 0. Simply meaning terms getting closer together. What do you think about that? You think that's true? And the answer is, yes it is. Why? Proof? I'll leave you to prove that, okay? And if you can't do it yourself, there's a proof in the book. All right, so this is true. Question. Is the converse true? If the limit as n approaches infinity of c sub n plus 1 minus c sub n is equal to 0 is the limit as n approaches infinity of c sub n going to exist? If terms are getting closer and closer and closer together, does that mean that the sequence is going to have a limit? And the answer is no. Not true. This is not true. There are sequences where the terms do get closer and closer together, but they do not have a, and I'll give you 2 examples. Consider this sequence. The square root of n. Very simple looking sequence. Question: does it have a limit? And the answer is no. Terms are getting bigger and bigger and bigger. So that one has no limit. It diverges. But what we're going to show is that this is true. That the terms are getting closer and closer and closer together as n gets bigger and bigger and bigger. And yet there's no limit. To prove that, let's look at c sub n plus 1 minus c sub n. N plus first term, square root of n plus 1. Nth term, square root of n. Now I don't claim that that's obvious, that if I look at that the terms are getting, that difference there is getting closer and closer to 0. But if we pull that same trick a minute ago, where we did that rationalization, suppose we write this. And we multiply that by the square root of n plus 1, plus the square root of n, over the square root of n plus 1, plus the square root of n. If we do that, what does the top become? It becomes n plus 1 minus n over the square root of n plus 1, plus the square root of n. And these n's cancel. So you get 1 over the square root of n plus 1, plus the square root of n. Does that get closer and closer to 0? As that gets larger and larger and larger. Do those get smaller and smaller and smaller as that gets bigger and bigger and bigger? And the answer is yes. So these guys do approach 0. These terms get closer and closer and closer together, but there is no limit to the sequence. So again, if the limit exists, the terms get closer together. If the terms get closer together, there may or may not be a limit. All right? Here's another example I'll let you prove. The logarithm of n. Clearly, no limit to that sequence, but I leave you to prove that the terms do get closer and closer and closer together as n gets larger and larger and larger. You can kind of see that if you think about it graphically. What does the log graph look like? Starts here at 0 and it goes like that. Right? And it goes up forever. But if you look at the terms of the sequence, there's the first one, the second one is that dot, the third one is that dot. Are these dots getting closer and closer together? That is. That, you look at that difference, and then you look at the difference between height of this one, then you look at the difference in height of that one, and that. Is it clear to you that those differences will be getting smaller and smaller and smaller? The answer is yes. But there is no limit to the sequence. Clear? There's material in this section. Again, we're working in 10.1. Applications, 2 numerical applications, Newton's method for solving equations, and a method called successive substitutions. You are not responsible for those applications. I'd like to do it, but time does not permit. So no Newton's method, no successive approximations. Which means then you can't do all the exercises in this section, and I'll tell you the ones that you should do. So in section 10.1, exercises are followed. Do these ones. One through 31, 56, 57, 58, and 61 through 66. You can do all of those based upon what we've talked about in these first 2 classes. But if you want to learn about Newton's method or successive substitutions, be my guest. It's good for your soul to see those applications, but you're not responsible for that. That finishes 10.1. Next section, 10.2, which talks about sequences of, not numbers, sequences of functions. So what a sequence of function is an assignment to every positive integer of a function. For example, notation would be something like that, instead of just f sub n or f of n, it's f sub n of x. Right? So an example, x to the n over n. This is a sequence of functions. To get a feeling for it, we might want to write out a few terms. The first term is x, first function. It's a function. The second term or second function is x squared over 2, x cubed over 3, x to the fourth over 4, and so on and so on. We actually saw a sequence of functions last day. I gave you that sequence, I gave you a few terms, and we wrote it in explicit form. It was a sequence of functions. Here's another very simple one. We ask of sequences of functions the same question we ask for sequences of numbers. We ask, do you have a limit? Right? So limits is what we're keenly interested in. Limits. But now there's two things that are here. Not only are there n's there, but there are x there. And what can happen is that a sequence of functions might have a limit for some values of x, but not for other values of x. And so you've got an added difficulty to say, not just, does this sequence of functions have a limit, but you're really asking, are there values of x for which this sequence of functions has a limit? That makes it somewhat more difficult to analyze. So here's my first example to ask you. If it does, you'd write, so if you had a sequence of functions, it's a limit as n approaches infinity, f of x. Right? So it would be a function because our x is in there, but it wouldn't have any n's in there once you take the limit. And so that's what we're going to ask you is, does a sequence have a function on some interval? So not only, so if somebody gives you the interval, then that's not a problem. But they might simply say, here's a sequence of functions, on what interval, if any, does it have a limit? So I'm going to do one example here, to start with. And I'm going to give you different domains or intervals on which to look at. So the sequences of functions are fn of x is equal to x to the n. Right? And the first interval that I want to look at is on 0 less than minus 1 less than x plus 1. Does that sequence have a limit on that interval? And you can look at it geometrically or algebraically. I didn't like too much the idea of graph for sequences of numbers, but they can be beneficial for sequences of functions. So let's graph a few of these functions in this sequence and look at the graphs and say, hey graphs, are you approaching anything? So if we look at a graph, we have an x-axis here, and then we'd have fn of x. And the first one is f1 of x is equal to x. Straight line. Going from minus 1 to plus 1, but non-inclusive, so we'll put little holes there saying, don't look at those. So there's the first function, it's graph. Second one is x squared. Parabola. It looks like this. 3 of x is equal to x cubed. It sits underneath the parabola. It's that, and it's that. X to the 4th for the 4th one. It's underneath again. That, and it's over here. So this was F1, F2, F3, F4. This was F1, F2, F3, F4. So look at those graphs and ask yourself the question. Are these curves getting closer and closer and closer to something as n gets larger and larger and larger? In fact, a sequence of functions defines an infinite number of sequence of numbers. For instance, you could say if x were equal to a half, then this would produce a sequence of numbers, namely 1 over 2 to the n. You can see those here. If you go to a half, if that's a half, then there's the first term in the sequence of numbers, there's the second one, there's the third one, there's the fourth one. And every value of x in this interval produces a sequence of numbers. And so when you're asking, does this sequence of functions have a limit? You're asking, does every one of these sequences of numbers have a limit? If it does, then that's the limit of the sequence of functions. If it doesn't, if there's at least one x for which there's no limit, then the sequence of functions does not have a limit, period. But is it true that every one of the sequences of numbers, no matter what, look at the difference between this and the sequence over here. Numbers are getting smaller, smaller, smaller. Over here, if you took minus a half, it's out down here, then it's up there, then it's down here, then it's up there. So it's not like this one where the terms are getting smaller. They're oscillating up and down, up and down, up and down, positive, negative, positive, negative, positive, negative. But is it true that no matter which of those sequences of numbers you look at, they all approach 0? That these graphs are approaching the function this. Hole here, hole here. That no matter which sequence of numbers you look at, they all approach 0. So we would be saying that the limit as n goes to infinity of this sequence of functions on that interval is the 0 function. The limit as n goes to infinity of fn of x is equal to 0 for minus 1 less than x less than 1. Is that clear? So the geometry can help you here. Didn't think it helped much back in 10.1, but it can be useful here. Right? Let me change the interval to minus 1 less than x less than or equal. So I add 1. And I asked you whether it's got a limit now. So all we're doing is the pictures would be exactly the same as this, but that would not be a hole, it would be a dot. All right? So exactly the same picture, but that being a dot. Does this sequence of functions have a limit? Does. Every sequence of numbers produced by the sequence of functions have a limit from minus 1 to plus 1 inclusive. And the answer is yes. The limit function now is hole here, cross here, dot there, 1 high, hole there. That's the limit function. So it does have a limit function, but this time it's not continuous. That was continuous. It was simply the x-axis, the 0 function. Now it's 0 everywhere along here, but a dot there instead of a hole here. So limit exists, so this time, limit as n goes to infinity of f of x is equal to 0 or minus 1, less than x, less than 1, and it is 1 and x equal to 1. So the limit still exists. We don't have to have a continuous function, so it exists. Third possibility. Suppose now I include minus 1 as well. What now? Is that graph exactly the same? The answer is yes. It still has this dot here, but now these become dots also. Does the limit exist now? Do all the limits of the sequences of numbers produced by the sequence of functions have a limit? And the answer is no. There is no limit at x equal to minus 1. At minus 1, what is the first term is? Minus 1, up to 1, down to minus 1, up to 1, down to minus 1, up to 1. There's no limit. So now, no limit. It fails to have a limit at one of the values of x, so we have to say no limit, period. See the difference? One last one. Same functions, but consider x greater than or equal to 0. So graphically, none of this is here. And these ones get extended forever. Is there now a limit? And the answer is clearly no. That when x is bigger than 1, what happens? Dot, 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 dot. They just keep getting bigger and bigger and bigger. No limit. Not just one point where there's no limit, like in C part, but half the pies don't have a limit. From x greater than 1 up to 2. Or I should say half of them, right? I didn't stop at 2, I went forever. So there's only a limit between 0 and 1. Past that, no limit. Right. So that's a fairly straightforward example, and it helped to draw the graphs to kind of see this geometrically as opposed to algebraically. I'm going to do one more. Consider this following. Limit as n goes to infinity of 3 to the n plus 1, x to the 4th plus 2 to the n x squared plus 11 over 3 to the n x squared 5x and 55. I've seen limits like this quite often on exams. Let's only do it on the interval 0 to 5. This one you have to be very careful about because there's a way that you can go wrong. Now, if these had been, say, like n cubed and n squares, you probably might have taken the idea from our previous ones of concepts. Let's divide by the highest power of n. That's the kind of thing you saw in first year, the kind of thing we saw last day. Here you might think, well, the counterpart, why don't we divide everything in the top and everything in the bottom by 3 to the n, right? If we did that, we would get the limit as n goes to infinity of. Divide that by 3 to the n, 3, x to the 4th. Divide this by 3 to the n, and you get 2 over 3 to the n x squared. Divide this by 3 to the n, that. So there's the numerator. Bottom. Divide by 3 to the n, x Divided by 3 to the n, 5 over 3 to the n, x. Divided by 3 to the n, 5 over 3 to the n. Now let's look at each term individually. What does this one do? Well, 2/3 to the n is kind of like this thing over here. If x were 2/3, you'd have kind of this scenario. But you don't have to say that. You simply say, this says multiply 2/3 by 2/3 by 2/3 by 2/3 10 times, and let the number of times you do it get bigger, bigger, bigger. Now clearly, it's going to go to 0. So this one goes away. Well, this one obviously goes away. That one obviously goes away. This one obviously goes away. You say, ha! I have 3x to the 4th over x squared. The answer then is 3x squared. And you blew it. If that's your final answer, you're wrong. And the key is, what did you do in going from here to here? In going from here to here, you canceled x squareds. You divided the top and bottom by x squared. You can't do that if x is 0. Are we allowed to talk about x equals 0? Should we talk? Yes! Okay. It said, you consider this sequence on that interval. So you must include x equals 0, and that's not correct for x equals 0. So you should be saying here, x not 0. And you could consider x equals 0 separately. Well, let's look at it. When x equals 0 terms in sequence are what? Put in x equal to 0. 0, 0, 0, 0, 11 over 55, which is 1/5. So at x equal to 0, all the terms are 1/5. Remember, that's not a number. That's every term in the sequence is 1/5. What is the limit of the sequence, all of which terms are equal to 1/5? And the answer is 1/5. So this is the answer for the limit if x is not 0, and when x is 0, the answer is 1/5. So we should be writing that the limit as n approaches infinity of that stuff, which I don't want to write it all again, is equal to 3x squared for 0 less than x less than or equal to 5, and it is 1/5 when x is equal to 0. Be careful of that. I've seen people miss that so many times. Be careful. Right. I had 2 more examples I wanted to do. Unfortunately, I didn't think I was going to get this far. So one will have to wait until next day, because I wanted to bring in some pictures. But I can talk about the other one. Consider this sequence. Fn of x is equal to absolute x to the n over n factorial. And I asked, does this sequence have a limit? Or for what values of x does it have a limit? I claim, because you can see that, it's obvious that x are between -1 and +1. Even if you include them, is that obvious to you that for those values of x, the limit would be 0? Because the numerators keep getting, or the denominators keep getting bigger, bigger, and bigger. And what do the numerators do? Well, if x is in here, and you put those x's in here, they're going to get smaller, 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 smaller. And you divide by bigger, 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 they're going to get smaller, smaller, smaller. If you put in 1, then this becomes 1 over n factorial. Well, as that gets big, that goes to 0. If you put in -1, this becomes the same thing, right? So in other words, for those values of x, it is clear that the limit is 0. But what if x is bigger than 1 or less than -1? For instance, suppose, for example, x is equal to 1,000. is this sequence of numbers that you produce by putting in x equal 1,000. You have 1,000 to the n. So Fn of 1,000 is equal to 1,000 to the n over n factorial. Does that limit have that sequence have a limit? The answer is yes. Now there's a proof in the book for any value of x, but let's just kind of illustrate the ideas with this 1,000, just to give you the idea why. And then when you look at it, you say, it doesn't matter whether it was 1,000 or whether it's 10,000 or whether it's 5. The same idea is going to be there. Let's write out the terms in Fn of 1,000. The first term is, put in 1,000 over 1 factorial. The next one is 1,000 squared over 2 factorial. 1,000 cubed over 3 factorial. And on they go. Now when you look at those, you've got to say to yourself, those numerators are getting huge. And the denominators are growing, but not nearly so quickly. But watch. Suppose I go out here to, say, the 1,000th term. If I went to the 1,000th term, I'd have 1,000 to the 1,000 over 1,000 factorial, right? Big number. Big number. All right? Let's look at the next one. If you look at the next one, you get 1,000 to the 1,001 over 1,001 factorial. Who's larger? This one or this one? What you've done in going from here to here, you've multiplied the top by 1,000 and you've multiplied the bottom by 1,001. It's smaller. If you go to the next one, you get 1,000 to the 1,002. You multiply by 1,000 again, but now you divide by 1,002. From now on, the terms are going to get smaller and smaller and smaller and smaller. And they're going to go to 0. Because the top bottoms are going to get bigger much faster than the numerators eventually. So they will approach 0. So the limit of this function, sequence of functions, the limit as n approaches infinity is equal to 0 for all x. When it comes to series of functions later on, I will need this fact time and time again, that no matter what x is, the limit of this sequence is 0. Every x whatsoever. All right? So let's leave it for today. Next day I'll consider that one example left over, and then we'll switch to series of constants, series of numbers, rather than sequences.